This is the first of an 8-video series on rational expressions. General concepts. First of all, what is a rational expression? Well, an expression is anything in mathematics that has symbols, and rational comes from the word ratio, which is basically a fraction. So when you think of a rational expression, think of a fraction, but don't necessarily think of it as a fraction of numbers. It could be a fraction involving algebraic symbols as well. So these are examples of rational expressions, essentially fractions in algebra. Now in this series of videos, we're going to be doing lots of different problems. In video 2, we'll learn how to simplify this expression into this one. It's called the reducing of a fraction. In the third video, we'll learn how to multiply rational expressions, and we'll see that this is the result. In the fourth video, we'll divide. Here's the result. In the fifth video, we'll learn to add, which seems like a strange order, but addition is actually harder than multiplication, so I saved that for the fifth video. Here's the result. In the sixth video, we'll learn to subtract. Here's the result. In the seventh video, we'll learn to do a mixture of problems all put together. We've got addition, subtraction, and division all melded together in this one. We call these complex rational expressions, which, side note, has nothing to do with complex numbers. It just indicates that they're complicated. Here's the result. And in the last video, we'll learn how to solve equations that involve rational expressions. This equation turns out to have two answers, as we'll see in a later video. But I want to re-examine a couple of those things that we just saw and look at them in a certain perspective. Just to warn you ahead of time, this video is not teaching you the mechanics of how to do a problem. The purpose of this general concept video is just to give you an idea of what rational expressions are so that you have a broad base to understand video 2 through 8, which are the actual mechanics of specifically how to do problems. Back to the basic idea. Does x have a value in all of these rational expressions? Is x a specific number? Well, let's take one of the examples that we're going to see in a later video. Now, you probably don't have the algebra mechanical skills to know why this thing simplifies to x minus 5, and I don't expect you to now. If you did, you probably wouldn't be watching this video. But it's worth analyzing what that means. Does x represent an actual number in rational expressions? Well, generally the idea is if there's no equation, then x could represent any number. And there's no equal sign in this problem. So for example, x could represent 100. By the way, I'm not suggesting that you should plug in random numbers for x. I'm simply showing you what would happen if we did. Now, if we were to pick some arbitrary number, say 100, and plug it into all the x's in the problem, we should get the same answer as if we were to plug 100 into the simplified version of this, or the so-called answer. Of course, that's 95, but it turns out if we were to work out this big ugly expression on the left, if you did all the mathematics using either a calculator or lots and lots of scratch paper, that actually would work out to 95. Again, I'm not suggesting that you should plug arbitrary numbers in for x. I'm simply addressing the question, does x have a value in rational expressions? Well, if there's no equal sign, it's assumed that x can be virtually anything. But we don't think about the specific things it could be. But x, in a sense, represents virtually any real number. That kind of problem we call a simplifying problem. Let me contrast that with this problem, which has an equal sign in it. Notice the equals 5. This is the one time in the study of rational expressions where x does attain a specific value, or in this case, values. It turns out this is a true statement when x is 4 or when x is negative 3/4. So to show you what would happen if I tried to let x just be some random number, or arbitrary number such as 100, if I were to put 100 in for all the x's here, I did some math on scratch paper, didn't show it in this video, and then I reached for a calculator and converted that to a decimal and just analyzed, does 1.08975 equal 5? Absolutely not. Well, what does that mean? That means that x equals 100 is not a solution to this problem. In fact, as we'll see in video 8, the solutions to this problem are x equals 4 and x equals -3/4. So having an equation in your rational expression problem changes the notion of what x is to x must be something specific for this equation to be true. We call that a solve problem, and we say that x equals 4 and x equals -3/4 are the solutions. Let's take a look at one more problem. This is one that we'll see in video 2, reducing fractions. So at this point, you don't know, more than likely, how it is that I simplified this expression to x over 2. But again, if I were to plug in 100 for the x's, if x over 2 really is the, quote, answer to this simplification problem, I should get the same answer for this big ugly mess here as if I were to plug in 100 for x in the simplified version. Now clearly 100 divided by 2 is 50, but guess what? The other thing works out to 50 as well. Now I didn't show the work here, but if you were to take a calculator or lots of scratch paper and work the expression on the left, you would in fact get 50. And this really illustrates what the meaning of simplification is. To say that this original problem simplifies to x over 2 means that whatever number I were to plug into the complicated original expression, I should get the same answer as if I plug that number into x over 2, as shown here with the specific example of x being 100. The question is interesting to ponder, though. Would this work for any number? Strangely, the answer is almost. It turns out this would work for any number except x equals 3. That seems strange. Let me explain. It turns out if we tried to plug in x equals 3 to this expression, notice I've put a 3 for every x. If we were to plug in x equals 3, something strange would happen. The top and bottom of this fraction would work out to 0. And as you may recall from previous mathematics, when the bottom of a fraction works out to 0, by the way, there's nothing wrong with the top of a fraction working out to 0, but when the bottom of a fraction works out to 0, we say that the division problem isn't doable, or we say that it's undefined, or we say that it doesn't exist. In other words, this division, this ratio, doesn't have an answer or doesn't exist because when x is 3, notice here, when x is 3, this denominator works out to 0, making it a non-existent fraction. So when we say things like the expression on the left simplifies to the expression on the right, we generally mean that any number we could plug in to the expression on the left would give us the same answer as if we plugged that same number into the expression on the right. Now, we just saw that this is not true when x is 3 specifically, but we generally tend to be kind of loose with our terminology, and we say that these expressions are equal to each other when we really mean they're equal to each other whenever they exist, but they're certainly not equal to each other when x is 3. Okay, those are the general ideas that you'll need to have in your mind when we go on to video 2 through 8, where we'll learn the actual mechanics of the algebra needed to simplify and solve rational expressions and equations. And that concludes the first of 8 videos.